Hi everybody, this lesson is about angular momentum and then going on to conservation of angular momentum. So just like how moving objects that are moving in a straight line have linear momentum, rotating or spinning objects have angular momentum. The symbol for angular momentum is the letter L. Now, there are two types of rotational motion. You could have a spinning object, just like the Earth spins on its own axis, where the axis of rotation is within the object itself. And in those cases, the formula for angular momentum, just like linear momentum is m times v, angular momentum, the rotational equivalent for mass is rotational inertia, and the rotational equivalent for velocity is angular velocity. So the formula for angular momentum is I omega for spinning objects. You could also have orbital motion, like the Earth going around the Sun or the Moon going around the Earth, or you think of a point on, say, a Ferris wheel or a merry-go-round, a point on the rim that is orbiting around. So that's orbital motion. So for orbital motion, it's mvr. So you've got two slightly different formulae for angular momentum, so it could be either. So what do all these letters stand for? So the letter I stands for rotational inertia, and you've got omega, you've got L, you've got M, you've got V, and you've got R. Now just write down what the units are. The rotational inertia is measured in kilogram meter squared. Omega is angular velocity or angular frequency. It's measured in radians per second. L is angular momentum. I'll come to the unit for this in a moment. Okay, it's actually just putting these two together. So it's kilogram meters squared per second, and mass is measured in kilograms, V in meters per second, and R is in meters, which is the radius. Okay, so it's just combining those three together, or those two. Radians does not have any dimensions, so it's just that. And that's how you come to the unit for angular momentum. Okay, why we're learning, so this angular momentum can be used for conservation of angular momentum, which has to do with spinning or rotating objects. So just like when you learned conservation of linear momentum, there was a condition, so it's provided there were no external forces for linear momentum. But for angular momentum, don't use the word force, it's better to say provided there are no external torques, then angular momentum is conserved. Okay, so there's loads and loads of examples for this. So if you have something that's spinning and you drop something else onto it, so what's happening is the angular momentum stays the same, but when you drop something onto it, what happens is its rotational inertia changes because there's a change in mass distribution. And so what happens is that the angular velocity changes. However, the product of angular velocity and rotational inertia should be the same. So like if you have a spinning, we usually have one of these little, it's got ball bearings, and this thing is spinning, and you can drop like a sandbag. You set it spinning, you drop a sandbag on it, and it's going to spin slower. Okay, so it's to do with I omega. So you got I1 omega 1 equals I2 omega 2, because angular momentum is conserved, but each of those could change depending on how the mass distribution changes. The other thing is, if you are sitting on a spinning stool or a spinning chair and someone sets you spinning, you hold your arms out, you're going to spin slower. You bring your arms in, you're going to spin around faster. So the way you explain this is again due to conservation of angular momentum. So angular momentum stays the same whether your arms are out or whether your arms are in. However, when your arms are in, your mass is closer to the axis of rotation. So note the language that is used. So because it's closer to the axis of rotation, your rotational inertia decreases. So your angular velocity increases. Okay? However, angular momentum is the same. When you hold your hand out, out. Then what happens when you spread your hands out is, and it's even more effective if you've got some dumbbells or something in your hand, because then there's more mass outwards, and you see that you're going to spin slower. Again, angular momentum's conserved, but when you put your arms out, your mass is further from the axis of rotation, so your rotational inertia increases, but your angular velocity decreases. However, the product of the two are still the same because angular momentum is conserved. Okay? And then there's the other thing about helicopters. So helicopters have got rotor blades, the spinning, the blades on top, as well as it's got rotor blades at the tail. So if those rotor blades were not at the tail, there was only the ones on the top, then the whole body of the helicopter would swing around when the helicopter only had one. So the rotor blades at the top, because angular momentum is conserved, they spin in the opposite direction to hold the helicopter steady. So, and then the other one is about divers. So to do somersaults, what do? So if you're on a diving board, jumping off the diving board, but you want to spin around a few times before entering the water, what you do is they tuck their bodies up into a little ball so that their rotational inertia decreases because their mass is closer to the axis of rotation. So if your rotational inertia decreases, angular momentum is conserved, so they can spin, do more turns, more somersaults before entering the water. And then they straighten their bodies before just landing the water, because then what's going to happen is their rotational inertia is going to increase because their mass is further from the axis of rotation. So I hope all that helped. Bye for now.